Okay, good afternoon, everybody, and I'm going to start our lecture. And I'm going to share. Okay. I don't know what's happening. However, I'm here. I am reconnected to the meeting. Can you hear me? Yeah?
Yeah.
Okay. Okay. So go to the presentation. Okay. And okay. So oh yes. And yesterday we talked about the
Però credo che non stia presentando.
Can you see the screen? Yes or no?
Yes.
Okay. I have a problem with my video projector in the room. Excuse me. Excuse me, I had a problem with the video projector in the room. Okay, I'm almost ready. I have something from Montezuma today. I had 2, 3, 4 undesired situation. However, I'm here. Okay. So yesterday we started from this differential equation scheme like this here, and excuse me. Okay, this year we started by this problem, and after a boundary integral equation procedure, we obtain this equation here, giving the velocity potential as an integral everywhere as an integral of the velocity potential on the body. This integral formulation can be discretized, so obtaining a boundary element method formulation, which is this equation time domain. This equation can be solved directly or in a linearized form. First, yesterday, we proposed an algorithm for solving this A original formulation in within a nonlinear procedure. Essentially, we have divided the body surface in panel, in a number of panels like M here, M, and the weight in a number of panels like N. And this procedure is very popular and is also known as boundary element method approach. In the first proposal here, we have defined a set of coefficients like B, C, and F. We have used E for the domain function. However, we have B, C, and F coefficient. Theoretically, these coefficients are time independent because the domain is a moving domain. But if you assume that this motion as given by the body flexibility is small, you can avoid the dependence of this integral on the time variation of the domain, of the integration domain, and therefore this coefficient can be evaluated. Here lies an integral of g minus dg on the n and minus dg on the n, but on the weight, like f. Okay. What, for example, if you want to evaluate B to be practical, so if you want to evaluate BKM, for evaluating a BKM, you have to fix the K point here. For example, you have fixed this point, and you have to fix an M panel like Milan, like here. So whenever you have fixed a point K and the panel M, you have BKM. So fixing K in the green function, G function formula, fix the extra point like xk, practically the coordinate of this point K here, and then perform this integration varying x in the SM, like Milan domain. So you have to cover all the possible term of this matrix BKM. Of course, the reverse, by MK, if you invert the role of the centroid and the panel, you have to not expect to have the same quantity. And therefore, this matrix is not necessarily a square matrix at all. And the same is for CKM and FKM. This is just to make you confident with this kind of coefficient you have. Okay? Beside the this formula connecting phi and key is representing the boundary condition. Besides this formula, we have another formula for the velocity. In particular, you can consider this formula. Yesterday this formula here for the velocity, and you can discretize this in this way, so obtaining another discretized form for the velocity. Like this here. And therefore, if you have evaluated phi and delta phi, you put inside here phi and delta phi, and you have the velocity as a byproduct. After this consideration, we proposed an iterative algorithm for evaluating the potential flow, the potential velocity phi, and the velocity everywhere in this way. Starting from the initial time, t equal to 0, you can solve this equation in the number one step, in the step number 1. I'm sorry. I'm trying to recap what we have obtained yesterday, but I am fighting today with the destiny. I'm fine. I don't know what's happening. Okay. So, excuse me, we have this step 1, find phi at a time t equal to 0. So this is phi in 0, and this is in 0. Okay? And so for t equal to 0, we don't have any kind of wake term like f coefficient. So in this time, once you know the boundary condition key, you can evaluate phi simply inverting this matrix, 1/2 I minus c to the minus 1. Okay? After this evaluation, you can evaluate v, velocity, everywhere, and in particular evaluate tb at the trailing edge, and we can evaluate the wake velocity like this. Once you know the wake velocity, you can do two things. The first thing is determine the wake motion. In this way, start from the leading edge and move ahead backward the wake panel. And after this, so determine the geometry of the wake in this way, x in t plus delta t is equal to t plus v wake dot delta t, and move on this new panel your delta phi, so applying the last boundary condition on the wake. Okay, and do this anytime, reiterating for any time step, capital T, not T, capital T. Capital T, no, T. This is a physical time. Okay? Note that this vector we have introduced are time-dependent vector, and they are currently collecting all the m velocity potential and all the normal wash boundary condition key. After this, we are going to propose a linearized approach, which is the approach that we currently will consider in our application. Essentially, we want to find a connection, a matrix connection between our m by 1 vector with this m by 1 vector, the potential, as you know, the normal wash vector, and these two vectors are the Laplace transform of the time vector. In particular, phi tilde s is the Laplace transform of this time vector, and this output vector key s is the Laplace transform of key time vector. And what about the connection, the system relationship between this input and this output? The connection is given by this matrix. And now we want to determine this matrix. Okay? Well, yesterday I'm first assuming this linearized approach, the weight to be flat or planar. So generated by the trailing gauge line in the motion, during the motion. Okay? And so we have, so the wave geometry is not an unknown as in the previous formulation. Wave geometry is unknown here. Okay? Next. Second step. Consider in a time your wave panel here, and you know that excuse me, you have in this wake point x wave, we have a delta phi in a time, in the current time t. Now this delta phi value is related to the value at the trailing gauge. In particular, this value is equal to the value at the trailing gauge, delta phi trailing gauge, in previous time step, like t minus tau, and tau is currently representing a delay at the moment. The necessary time for the delta phi discontinuity for moving from the trailing gauge up to this point here. And the point is, how can we determine this time delay? For determining this time delay, we assume a linearized condition, and the linearized condition is the following. Imagine to consider a wake velocity. The wake velocity is a velocity in absolute frame of reference. In particular, in absolute means air frame of reference. Absolute. Absolute means that you are here on the earth and you are seeing the aircraft flying up your head. So look at the wake point. In my absolute frame of reference, I'm assuming that the wake is fixed. No velocity, no absolute velocity. Okay? This is exactly what you see when you see the sky and the wake, the combustion wake of your aircraft. You see the aircraft moving, but the combustion stays there, does not move in your frame of reference. This is the concept. And this velocity can be decomposed as a relative velocity, which is the velocity of the wake with respect to the body, in the body frame of reference, with respect to the body frame of reference, and the body frame of reference velocity. This both frame of reference velocity is equal. Look at the motion of your aircraft. The aircraft is moving in this direction, which is the opposite of your x direction in the body frame of reference. So in that reference, this velocity is minus I is the unit vector in the x direction by u infinite. And so you see, if you see this, you have that your wake velocity relative velocity is practically equal to minus, excuse me, the wake velocity is equal to plus I u infinite. And this means that if you are an observer fixed with the aircraft, you can see this discontinuity moving in the wake with the velocity equal to u infinite. Okay, so what about this time delay? This time delay, tau, for this in this point, is equal to this space length, x wave, which is currently the x coordinate of your delta phi point, divided by u infinite. Okay? And with this position, we have essentially closed the problem of our formulation. In fact, look what happened. We have that our formulation, this formulation, rewrite this formulation as 1 half phi k function of t is equal to summation m of bkm key m time. M is running from 1 to capital M. Again, you have C, summation C km by phi m time. Again, M is running from 1 to capital M. And now we have plus, and here we have to sum all the wake panel contribution, but we can say that this is valid, and you can write here fkn, you know fkn, summing n from 1 to capital N, and we have delta phi, but in the trailing gauge, like this TA, I moved this TA up and put down N, which is the index of the panel, but in T minus, what about tau? Tau is a delay which is dependent on the N panel in the sense that, look, tau N is equal to the wake point in the N panel, this N here, N equal to, I don't know, number 2, N2. So the delay time associated with the panel 2 for N equal 2 is equal to the x coordinate of the panel 2 minus the corresponding trailing gauge. So you have to consider this distance, I'll write later, divided by u infinite. This is the stupid evaluation of this time delay here. From here, let me use another color. From here to here, you have x wake n minus x trailing gauge. You have this number, you can write this number for each panel. So, for each panel n, you have a time delay. Write this. Therefore, for all n panel, you have a time delay tau m. Okay? Now, we need just stupid further information. We have to connect this delta phi value to the unknown of the problem with the delta phi, with the phi on the panel. So we introduce a S and M matrix. S is for stupid, and this matrix do the following. This matrix is such that the delta phi at the trailing edge for the panel N is correlated with all the potential velocity value on the body as a summation of n m by phi m. And how can you do this? For example, you have this, and this is, you have an example like this. This is n equal to 57, the panel, and you want to say that for this panel you have to consider this jump between, this is the m equal to 24, okay, and down you have m equal to 43, and you want to correlate this delta phi 57 with as equal to this here, this jump phi 24, excuse me, and phi 43, and you want to do phi 43 minus phi 24. What about S? Simple. You have to fill S. In order to have delta phi TE 37 is equal to phi 24 minus phi 43, upper minus lower. I have, this is not true. This is, excuse me. Delta phi is 24 minus phi 43. And how can we do this? You have just to choose S and M in such a way. In order to have S and M equal to 1 minus 1, 0. Okay? In particular, excuse me, 37 and 24 is equal to 1. S in this case, and S 37 and 43, yes, 43 is equal to minus 1. Okay, and the other 0. Okay, and the other better, the other you have to associate to one of this. Okay, so the other S37J are 0 for all J. So we have a simple operator, is a topological operator, able to connect the jump at the trailing edge corresponding to this panel in the same time. Okay? So this allows to you to write your integral equation in this way. You have 1/2 phi k time plus equal to summation b k m km time m capital M plus c km phi m time, and finally we have summation. Pay attention here, summation. In the previous equation here we have summation phi kn delta phi at the trailing edge in previous time. We are representing the actual panel in the weight, but we have related this panel to the value of delta phi at the trailing edge in previous time. Now we have the connection between the delta phi at the trailing edge and in general all the velocity panel, all the value of velocity potential on the body. So we have this n from 1 to capital N, and we have fkn, but instead of delta phi n in t minus tau n, we can write this summation, for m from 1 to capital M of the stupid matrix S and M applied to the velocity potential on the body. Most of these S are 0, and you have just to select upper and lower the trailing edge, +1 and -1, and this velocity potential is not at the present time, but is in t minus tau n. Okay, in previous time. And this is a delayed equation. And here you can see that this equation is able to relate what happens to the velocity potential in the present time t with what happened to the velocity potential in previous time t minus tau n. And you have several delays associated with the several weight panels. Okay? Now we have finished. We have just to take a Laplace transform of this linear equation. Okay? So take the Laplace transform, but okay, take the Laplace transform. Yes, Laplace transform. We have this. We have 1/2 phi tilde k, the Laplace transform of the velocity potential in the panel K, equal to summation of b km, the Laplace transform of the unsteady input boundary condition in any panel. Currently we have the unsteady value of the normal component of the velocity to the wall, to the aircraft wall, and plus C summation M running from 1 to capital M running from 1 to capital M, C K M, phi tilde again M T, plus we have a double summation F N from N to capital N, F K N, and S N, excuse me, we have a double sum, and so we'll emphasize this double sum here. We have summation and summation for M running from 1 to capital M, F K N like Naples, please, and S like Naples and Milan, by phi tilde M by E to the power, finally, S Laplace variable tau N. Okay? Because the Laplace transform of f function ft minus tau is equal to the Laplace transform of the function f as a function of t by e to the power s tau. Okay, I applied this here. Okay, the last concluding part of this expression, we have that if you move to the left-hand side, this we can move 1/2 phi tilde k minus, excuse me, minus, you can multiply this by a Dirac k m, you can write m here. This is redundant, but this is useful for collect the term of our summation. And we have also minus c k m by phi tilde again, and we have minus summation, double summation of n from 1 to n, and this is phi m from 1 to capital M, f k n, the stupid matrix, and I am moving this term, and this term, excuse me, I am moving this, I am moving this term, I'm moving, excuse me, this term here and this term here to the left hand side. And so I have this by phi tilde m e to the power s tau m, and everything, this vector is equal to b summation b km k tilde m. Okay, and therefore you can move this, look, you can take this here, here, and here, and you can, you can collect this summation. I forget to write the summation, excuse me. M, okay? And you can collect this M summation from 1 to capital M of a quantity, unique quantity applied to phi tilde M equal to summation of M B K M key tilde M. Inside here, you can see a matrix like Y matrix with component K, M. And this matrix is a function of S, is the following, is, look this inside, 1/2 delta Km minus C Km minus summation for n from 1 to capital N, F Km S N M. And this is Y. This means that you have that your Y matrix, function of S, excuse me, here you have e to the power S tau n. Do not forget this, this is essential. Is the unique dependency by S. This matrix, as applied to your phi tilde vector, is able to give you B matrix by key. This is a M by M matrix. This is M by 1, M by M, and M by 1. Are you right? Can you follow me? Okay. And so, phi at the end, the vector, is equal to Y matrix to the minus 1 by B by key. And so this is our operator. This is our promised operator, E2. This E2 operator is depending on Laplace variable. It's a strange transfer function with this exponential. And is this operator depending on the geometry of the wing or the aircraft? Yes, because the coefficient B, C, F depend on the geometry. It is dependent on geometry. Is this operator depending on the flight condition or not? Okay? But we have a but. So this is dependent parametrically on U infinite. However, look what happened here with this exponential. We have e to the power S. Oh, stupid. I'm very stupid. You have a minus sign here. Excuse me. Correct this. You have minus. Minus. This is the rule for the exponential. For the Laplace transform of delayed function. This is the rule. I am very tired. I'm sorry. So we have minus. Okay? However, the point is, when you have an argument of an exponential like this, what about the dimension of a transcendental function? The dimension of an argument of transcendental function, or also a sine function, or a logarithmic function. Yes, these arguments are non-dimensional quantities. Okay? Therefore, S tau n is undimensional, of course, and therefore, if you write S by X, you have a length here, X weight minus X trading age divided by U infinite. If you multiply for a reference length L, like L, or like the chord, this an undimensional quantity, representing an undimensional length, and this is an undimensional quantity as well. Typically, this L is the chord length, or half chord length in aeroelasticity. So let me write here L equal to the half chord. This is the very standard assumption in aeroelasticity. Chord by 2. However, this is an undimensional length, and this is an undimensional, this is the novelty, undimensional Laplace variable. Right? This is an undimensional group. Okay? And please let me define this Laplace variable like P define equal by definition to S by C by 2 divided by U infinite. Okay? Now, do you know very well that, so in this case we have that our transfer function E2 is function of S or U infinite, but if you introduce this undimensional variable like C S by 2 U infinite, this function is a function of P only. The dependency on U infinite is absorbed by this nu. Okay? As you know very well, if you put S equal to J omega, you move from Laplace domain to Fourier domain. And in this case, you have the concept of frequency response function instead of transfer function. You have a transfer function here, in Laplace domain, and you have a frequency response function here is a function of omega and u infinite. Okay, but if you assume that in general S is equal to a real part plus, how do you call the real part of the Laplace variable? Alpha? Never call? Okay, alpha, it's okay by me. And the imaginary part is omega. Okay? If you move this in a dimensional form, like S by C divided by U infinite by 2, this becomes alpha by C to unidimensional and plus J omega C divided by U infinite by 2. Now, Laplace variable, and Laplace variable has a real part and imaginary part. This imaginary part is currently the frequency of the Fourier domain, right? But if you consider this undimensional form, like P, defined before, you have an undimensional real part plus an undimensional imaginary part, also known as K. Okay? And this K is equal to omega C divided by U infinite by 2. Is any sophisticated aerodynamic people in the room at the moment? People who knows all the possible undimensional fluid dynamic number, Reynolds, Brandt, Nusselt, Weber, Strual. Strual. Did you ever seen Strual number? Anybody? Nobody?
Not yet.
Not yet. The Strual number is a number quantifying the unsteadiness in the flow, a frequency present in the flow. For example, a standard example of Strual number is in the famous problem of the cylinder. You know this problem with the flow with von Karman vortices, one here, one here, one here. Do you know this problem? No? No?
All right.
Nobody know the von Karman cylinder problem? Nobody? Okay. And for this problem, you have an alternate shedding of vortex. And so you have an intrinsic frequency in the flow. Okay? And this frequency of this phenomenon is related to the velocity. If you increase the velocity, the flow, the frequency of the vortex exchange, but the ratio between the velocity and the frequency keep the same. So you have a characteristic undimensional frequency given by this ratio here. We will interpret this, and this quantity is very important in aeroelasticity. Okay? And you have realized that this quantity naturally is generated by the problem. Okay? What time is it? We are a bit in delay. However, the last concept is the following. Your frequency response function is in general a function of the frequency omega and of the velocity. But if you introduce the reduced frequency, this frequency response function metric function only of the reduced frequency EK. And I stop here. Okay?
se può dire il numero iniziale del prodotto, perché
non lo riesco a fare molto. Quindi siete una moltitudine silenziosa.
Professore,
Sì.
ma il fatto che poi comunque abbiamo dei termini trascendenti non ci dà problemi dopo nella risoluzione del problema, dal punto di vista computazionale parlo.
In che senso? Qual è il problema dei termini trascendenti? E elevato alla S è una funzione ben definita, complessa di variabile complessa. Qual è il problema? È una funzione complessa di variabile complessa. Il problema che dà?
No, stavo rivedendo così, cioè non ci abbiamo grosse problematiche.
Non ne vedo. Non ne vedo.
Ok.
Legate a cosa? Che cosa c'è in mente? Causalità?
Scusi?
Mm?
No, non ho capito che ha detto, scusi.
Causalità, no casualità, causalità. Sai che cos'è? No, se
La
sa
ca-
manco che
ca-
cos'è non ce l'ha il problema. Non è un problema. È una funzione di trasferimento. Qual è il problema? Tra l'altro ricordiamoci che l'abbiamo messa pure al denominatore, perché abbiamo fatto l'inversa poi. Non ci abbiamo la S, ci abbiamo tutta quella roba che poi va invertita. E poi non è una dipendenza da un ritardo, cioè avete tanti ritardi per ogni pannello,
Sì, certo.
vengono combinati. Quindi è una cosa complicata che la fai computazionalmente una volta, la metti nel calcolatore e l'hai trovata. Ok?
Sì, sì.
Adesso ne riparliamo, perché adesso siete poco proattivi. Ok, vogliamo riprendere? Let's go. And okay. So after this process, we have defined this matrix. Why? In this way. We have defined this matrix B, which is currently the matrix of the integral of the source in the panel versus the fixed point. And the inverse of this matrix by B is our E2 matrix. And this E2 matrix is the operator. Now, the interesting point is that, remember, do not forget the scope. And the scope is the following. U, displacement, in Laplace domain, like x and Laplace, is almost equal to summation, mode shape, approximated mode shape by function of x, by and by q bar tilde vector function of x Laplace domain. So I'm using this Lagrangian coordinate, model Lagrangian coordinate, and I will represent the motion in Laplace domain with s square and diagonal model mass, k diagonal model stiffness applied to q bar tilde, this vector, is equal to 1/2 rho u to the power 2. This is the dynamic pressure. And here we have E4 matrix, E3 function, E3 matrix, E2 matrix, E1 matrix, and finally we have Q. And all this, all this is a unique E matrix, function of S. And at the moment, we have studied this partial operator. What is this? This partial operator, which is the operator transforming the normal wash in the velocity potential. This E1 operator will transform the modal coordinate in the normal wash, E1. E3 is actually transforming the velocity potential in pressure coefficient. And the final one is able to transform the pressure coefficient into the generalized force. What is it? As here you have QD, which is a coefficient, by E. E are the generalized force. Remember, you have to project the pressure on the mode for having EM. And so the last step here, you have the generalized force. So we focused on one specific part on the aerodynamic operator, the potential part, transforming the boundary condition, the wall boundary condition, into potential flow, into velocity potential field in the panel. We will describe other steps like the transformation. For example, here, do you have an idea about the nature of this E3 operator transforming the velocity potential into pressure or pressure coefficient? Which is the physics? Which is the equation able to transform velocity potential in pressure? Yes, and therefore E3 will be an operator discretizing the Bernoulli theorem, and so on. Now this is our job in next days, okay? Okay, but I want to continue this part, not now. Now I want to spend with you time with the exercise, a practical exercise, a model which will be able to give us an idea of what happens in a numerical point of view in a simplified version. And the model is the typical section model that I want to introduce to you for introduce the exercise number 2. The numerical exercise number 2. And the model is the following. You have a typical section like this, and this section is elastically connected with a point here. You have a point of this section which is elastically connected and also elastically connected in a torsional point of view. In the undeformed, in quote, deformation, this airfoil is here in the undeformed configuration. So this is the deformed configuration, and in this deformed configuration you have a vertical displacement and a rotation. Okay, and this is let me check just a second, I think. Okay, and what we have is the following. We want to choose a point like this as main degree of freedom, and this rigid body in this plane, the section is rigid, and therefore the elasticity is given only on the elastic constraint of the airfoil to the undeformed configuration. So essentially you have a rigid body in this plane 2D, and initially you have 3 degrees of freedom for a body in a plane, 2 for the translation and 1 for the rotation. But what we are describing? We're describing essentially the motion of a wing, and therefore we have for a section, that's the way to the name of typical section. For a section you have translation, and the translation is associated with the bending, and you have rotation, and the rotation is associated with the torsion. But indeed you have also a translation in this direction, and this is another bending degree of freedom, but this is a bending on the plane. But what about this bending stiffness with respect to this bending stiffness. You have typically a wing box like this. You have a wing box like this. And therefore, the elasticity with respect to this neutral axis, with respect to the bending with respect to this other neutral axis, you have, and for this you have EIX, and for this you have EIY. Excuse me, you have EYX and EI zeta, because Y is the dimension of the span. So typically, the stiffness of this out of plane, imagine to have the plane of the wing. So you have an out of plane bending and in plane bending. The in plane bending is a more rigid motion, and therefore we can assume practically to be the wing infinitely rigid in the plane. This is more and more stiffening with respect to this here. And for this reason, we consider only 2 degrees of freedom. Currently, vertical motion, or also known as plunge motion, plunge or heavy motion, and pitch rotation. And therefore, our degrees of freedom are the following. We can consider the heave motion like this H, positive down, this H, and after this translation you have a rotation around here, and this rotation is alpha. So you have 2 degrees of freedom, H and alpha, representing the dynamic of this section. H is a function of time, for example, and for time. So if you take this and put down and rotate and release, you are describing in a simplified way the dynamics of a wing. Okay? But now we are mature person, and therefore I can state the following. The generic displacement of the wing of this section is equal to ht by 1 plus alpha function of t by x. What does it mean? It means the following. If you want to represent this function, continuous function of ux in a time, the displacement field. The displacement field is summation of this constant here, red line, plus rotation. Of course, this dynamic is linearized. But now I have for you this interesting issue. Look. Francesco, I'm teaching. Excuse me. Sì, ciao. So this is a special Lagrangian representation of the motion. Now we have currently two Lagrange equations of motion like this. This is Q1, and we have alpha, which is the second one, Q2, and we have two shape functions, interesting shape function. This phi1 is the constant shape function, or you have a shape function constant like this. And this is one. This is -1 value. And here you have this shape function around this point 0, which is the origin. The origin of the frame of reference. And so we have this. You have this shape function here. Okay. Interesting. Very interesting. Note that the positive displacement is down, is not up. Okay. So this is positive direction. And so I can directly apply my concept on Lagrangian dynamics. So I can define and introduce a mass matrix, a stiffness matrix, and so on. These coordinates are not coordinates representing direct displacement. One is representing the displacement, the other one is representing the rotation. They are not modal coordinates. They are just the first coordinate I have in mind for representing my motion. Okay. So in this coordinate system, we have that the displacement of the center of mass, like G, is equal to, excuse me, if you want the displacement of the center of mass, you have to put, instead of x, the coordinate of center of mass, and then the time, and therefore we have that ht plus alpha t by the coordinate of the center of mass. And this offset is the coordinate of the elastic center. The elastic center is the point when you have fixed the springs. Okay? And here you have the center of mass in the format configuration like G here. This other offset. Just to be sure that this elastic center is something similar to the shear center for a box. What is the concept of shear center? It's a special point such that if you apply a force, vertical force at that point, the wing or the beam simply translates, but it does not rotate. If you push in the point E, the wing, considering the spring, the wing will translate without rotating. Okay? And if you indicate with U, where are you? Okay. With U in the elastic center, T is equal to H plus alpha x E, and correspondingly for the velocity you have U dot at the center of mass, is equal to the time derivative of h plus the time derivative of alpha by xg. Okay, with this two or three expression like this, and this, we are able to represent the kinetic energy as a function of Q1 and Q2, and the elastic energy as a function of Q1 and Q2. Remember that Q1 is h, and Q2 is the alpha rotation. In fact, what about the kinetic energy? The kinetic energy, you can use the Huygens theorem, and this kinetic energy is the energy associated to the motion of the center of mass. So you have 1/2 m is the mass, m is the mass per unit length of the wing, length in y direction, and so we have 1/2 m u dot g. This is u dot g. This here. This is ug, and this is ue. So you have 1/2 m u dot g to the power 2 plus 1/2 rotation to the power 2 by the moment of inertia with respect to the principal moment of inertia. Okay? But u dot g here is this. And so we have 1m h dot plus alpha dot xg to the power 2 plus 1/2 alpha dot to the power 2 jg. Okay, and so we have the kinetic energy as a function of h and alpha. Better, function of h dot and alpha dot. The same for the elastic. For the elastic, we have 1/2 the constant of the stiffness associated to the translation k. We have a kh, a k alpha. K alpha is the stiffness of the protection of the torsion spring, and k alpha is the stiffness of the translation. And so 1/2 kh. Here I have to use ue, and so we have h plus xe alpha to the power 2. And this is the elastic energy associated to the vertical spring, and plus the elastic energy associated to the torsional spring. And so we have 1/2 k alpha by alpha dot to the power 2. No alpha dot, excuse me. Not dot. Oh, what happened? No. Mi sto domandando come ho fatto a perdere tutto quello che ho scritto. Okay. Don't worry, I will rewrite everything. Okay. What? You do what?
Sta dicendo di provare a fare l'undo, professore.
Undo? No, doesn't work. No. Oh my God. Is anybody making macumba with you? Io non capisco. Excuse me. No, manca tutto il lavoro che ho fatto qui. Okay, don't worry, we have the movie and I will rebuild everything by the movie, okay? And not worry. Not worry. This is the version, look, this is the version of 10. It's very, I know no word for describing this. I don't know what has happened. Okay, no, don't worry about this. I will recover this part. However, I write here as a new geograph for you, and the final idea is that we have E and T, okay? And E is the elastic energy, the total elastic energy, as equal to 1/2 kh by h plus xe alpha to the power 2 plus 1/2 k alpha 2, and then I have 1/2 m h dot plus alpha dot xg to the power 2 plus 1/2 alpha dot to the power 2 jg, which is the principal moment of inertia. Okay, the Lagrange equation motion can be obtained here by evaluating first the derivative of the kinetic energy with respect to first h dot, and we have this derivative here, so we have m by h dot plus alpha dot xg, and by 1, because I have derived this with respect to h dot, so I have 1. And nothing here. Okay? The other derivative is the derivative of t with respect to alpha dot. And we have m, h dot again, plus alpha dot xg, but now I have by xg. Take the time derivative of this, and we have m h dot dot plus alpha dot dot xg And here, deriving this with respect to the time, we have mh dot by xg plus alpha dot by xg to the power 2. Okay? As a very final part, we have the derivative of E with respect to h dot, excuse me, with respect to h. Look here, and we have kh by h plus xe alpha by 1. The derivative of h with respect to h is 1. And the last is the derivative of the elastic energy. Bene. This derivative with respect to alpha is equal to k alpha by h plus xe alpha by xe. Very final equation are the Lagrange equation of motion. In the other sheet here, we have the time derivative of t with respect to h dot minus t with respect to h, but we don't have this dependency, plus the derivative of E with respect to h equal to the generalized force. And second equation, the derivative of t with respect to alpha dot minus the derivative of t with respect to alpha, we don't have this, plus the derivative of E with respect to alpha equal to E alpha. If you recast this, you have this final equation, and that's it for today. You have mxg, mxg, mxg to the power 2 plus jg, and this is applied to the vector h dot dot alpha dot dot plus, and I have collected this part here, now excuse me, this part, wow, this and this, okay, and finally kh xe, kh xe, kh xe to the power 2 plus k alpha applied to h and alpha equal to the generalized force on h, the generalized force on alpha. And these are the two equations of motion associated to this. This is a naturally discretized problem. So you have naturally discretized problem. We don't use a finite element approach. We are a rigid body elastically connected to ground, and that's it. Okay? There is no discretization problem in space. The system is naturally discretized in space because it's a concentrated parameter system. Okay? But the equations are the same. So this is our mass matrix, finally. This is our stiffness matrix, but these metrics are not diagonal because we are not using the mode of vibration for representing the system. If you consider, not this point is interesting, if you consider as vertical displacement the center of mass, you will have the mass matrix diagonal. If you consider the elastic center as vertical displacement, you have the stiffness matrix diagonal, but not the mass one. In order to have both diagonalized, you have to use the modal coordinate. Okay, and that's it. This is our toy. This is our toy next days. Okay, we will use this system. We will undimensionalize this system. We study this system with Carl. If you have an idea on how to recover my file, please welcome. I don't have any idea what's happening. However, I rewrite everything by the movie. Thank you.
Ma professore, io non credo che sia necessario che scriva tutto, tanto insomma possiamo vederlo noi il video.
Non ho capito, scusi, devo ripetere?
Che non è necessario che lei riscriva tutto, tanto possiamo vederlo noi il video.
No, ma io ci metto 3 secondi e siccome avete tutte quante le mie whiteboard caricate, io le carico tutte, non c'è problema.
Grazie mille.